Hello and welcome to another episode of Twiml Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Just a couple of quick announcements today related to the Twiml online meetup. First, the video from our December meetup has been posted and it's now available on our YouTube channel and at twimlai.com/meetup. It was a great meetup, so if you missed it, you'll definitely want to check it out. But you definitely don't want to miss our next meetup either. On Tuesday, January 16th at 3 o'clock Pacific, we'll be joined by Microsoft Research's Timnit Gebru, who will be presenting her paper, Using Deep Learning and Google Street View to Estimate the Demographic Makeup of Neighborhoods Across the United States, which has received national media attention for some of its findings. Timnit will be digging into those results, as well as the pipeline she used to identify 22 million cars and 50 million Google Street View images. I'm anticipating a very lively discussion segment as well to kick off the session, so make sure to bring your AI resolutions and predictions for 2018. For links to the paper or to join the meetup group, visit twimlai.com/meetup. All right, now a bit about today's show. In this episode, we hear from Siddha Ganju, data scientist at computer vision startup Deep Vision. Siddha joined me at the AI conference a while back to chat about the challenges of developing deep learning applications, quote unquote, at the edge. In other words, those targeting compute and power constrained environments. In our conversation, Siddha provides an overview of Deep Vision's embedded processor, which is optimized for ultra low power requirements, and we dig into the data processing pipeline and network architecture process that she uses to support sophisticated models in embedded devices. We dig into the specific hardware and software capabilities and restrictions typical of edge devices and how she utilizes techniques like model pruning and compression to create embedded models that deliver needed performance levels in those resource-constrained environments. We also discuss use cases such as facial recognition, scene description, and activity recognition. Siddha's research interests also include natural language processing and visual question answering, and we spent some time discussing those as well. And now, on to the show. All right, everyone. I am here at the Artificial Intelligence Conference in San Francisco, and I'm with Siddha Ganju, who is a data scientist at Deep Vision. And Siddha, welcome to the show. It was a pleasure to have you.
Hi, thank you very much. Thanks for having me.
Absolutely, absolutely. So why don't we start by having you tell us a little bit about your background and how you got interested and started in machine learning?
So I think I got started in machine learning during my undergrad days.
Okay.
So I had gone to a hackathon and I met this mentor there. His name is Anirudh Kaul. And we worked on a project there which was called Orphan Locator, which was basically trying to locate missing children using the police databases. And we used a very simple image matching algorithm there. So I think that was my first introduction to machine learning. Then after the hackathon, when I came back to college, I was like, I want to know more about it. So I think like everybody else, I started doing the Coursera course on machine learning.
The engineering course?
Yeah. I guess after that, I applied for a master's degree in data science. So I just graduated this year from Carnegie Mellon with a master's in data science. And then at CMU, I worked on what is called visual question answering. So that's an AI hard task, which basically provides an image to a computer, and a user or a human is expected to ask a question about the image. Now, this question can be about any activity or the number of people or something related to the image or the scene within the image. And the computer or the AI system is expected to provide an accurate answer to that question. Now, there are many uses of VQA or visual question answering. One is obviously for the visually impaired, but another use is for people in situationally impaired. For example, like if you're in a car and you're driving, so you don't want to be looking at your phone. So your phone can basically give you a description of the images that somebody just sent you. Or if you're a security analyst, then you don't have to comb through hours of video footage. You can just query, like, what did the man take from that shopping mall? So you can just, describe the situation sort of to a system, and the system can provide you those frames in which that happened. So these are some of the examples of VQA. And our research was focused on how can we use visual questions as a form of supervision for improving computer vision models. Because in the future, it'll become common for humans to ask visual questions to computers, like, where did I leave my keys? Or what breed of dog is this? Now, if you look at this question, there is a lot of information already provided in the question itself, like the object or the animal we're talking about is a dog, and etc. So that's primarily where the research was focused. Yeah.
Okay, interesting. And here at the conference, you did a talk, or I forget you're doing, or you did it yesterday. Right. Yeah. But that talk wasn't on VQA. That talk was
that was actually on embedded deep learning, which is how you can take deep learning algorithms, which are compute intensive, and they are pretty big in size, and how you can take them to embedded devices, because embedded devices have limited compute available and they have limited storage. So how can you run these algorithms at inference time on these devices? So this is basically the work that I'm doing currently at my company, Deep Vision.
Okay. And is that the focus at Deep Vision, or is that just one of the many things that the company's working on?
So that is the focus of Deep Vision, basically to...
Tell us a little bit about the company.
Yeah, sure. So the company was founded by 2 Stanford PhD graduates, Rehan and Wajahat. And the hardware or the processor that they developed was during their PhD itself at Stanford. And this hardware is basically, it has high performance per watt. At the same time, it is programmable enough so you can run a wide range of algorithms, which includes both traditional computer vision algorithms and deep learning algorithms on the same device itself. So if you look at most of the processor these days, if you want high performance, then it's ideal to develop what is called a custom hardware or a fixed function hardware, which is built basically for that one particular operation that you want. And on the other hand, if you want a broad spectrum device, which is programmable, so you can run a lot of things on it, it will be not as efficient as the fixed function hardware. And an example of programmable devices are the GPUs, or the graphical processing units. But these have a high cost, so they're expensive. And they're also really big, so you can't actually put them on embedded devices. So they were able to figure out a way to bridge the gap between performance and programmability, through which they developed this processor.
Interesting. And so does the company compete with or play in the same space as the Intel Movidius?
It's actually a little different because we are building both the hardware and the software. And I don't think Movidius follows that plan.
So, but the hardware is specifically focused, I'm inferring from the name Deep Vision, on visual types of problems and like CNNs, for example.
So we can run like CNNs, we can also run LSTMs on it. So it's not particularly just the convolutions. So yeah, like a broad range of deep learning basic systems can be run on it.
So why don't you walk us through your talk and the major points that you were trying to convey to the audience there?
Sure. So as I already mentioned about the hardware innovation, which is bridging the gap between the performance and the programmability. So one of the basic ideas behind this is that the convolution operation, that basically belongs to one of the classes of those computations for which it's possible to build efficient hardware when you build it in ASIC format or application-specific integrated circuits. So that's basically what they did. And they were able to basically optimize this convolution. Now, if you look at traditional computer vision methods, most of them have like an overlapping stencil or like a sliding window on which they run operations, which, if you think about it, is similar to a convolution. So, and additionally, it's also similar in like MapReduce operations.
Okay.
That's also like a window, and you're repeating the method over and over again over different windows. So this is basically how they got the idea to optimize this one particular class of functions. And it has wide applicability over traditional computer vision and deep learning algorithms.
Okay.
And the other thing that I mentioned in the talk was that why are we focusing on embedded devices or edge devices? And if we look at the data available for embedded devices, it's approximately more than 150 zettabytes of video data. So if you think about where this is coming from, like airport surveillance cameras,
Right.
traffic light cameras, basically all the cameras that you see anywhere, they have embedded devices in them. And they need someone to be looking at the videos right now. But it is a hope that these can be automated eventually. So that's where you will need these devices to be intelligent enough to perform real-time analysis.
So the idea is that you've got tons and increasing amounts of surveillance data all over, from security devices, smart city initiatives, down to home security, and eventually maybe our phone cameras will be always on. Right?
I don't know. Yeah.
There are some people worried about, scenarios like that. But in any case, there's just tons and tons of video data all over the place. And right now people are reviewing that manually, and the company is kind of building towards a model where you're training models to, identify various, features like, objects or people or things like that. And you would deploy those models out to devices, inference engines that live at the edge and can basically raise flags when different things are happening.
Yeah. One more thing is that the models that you train, like for home security, it will be different than for example, airport security, because in home systems, you need to recognize like 5 or 6 people, not more than that. But in airport, you need to recognize like thousands of people instantaneously. So the way of training the models and developing the models in both these scenarios is completely different. So we're also looking into how to train each one and how to make each one dense enough so that the model is extremely small, so that we can fit it onto these embedded devices. At the same time, they should be accurate enough that we are getting the correct results.
So you mentioned the number of people that you're trying to identify. So it sounds like one of the main use cases is, in the security scenario, I see this person, in this frame here, pull up other frames in videos where that person appears. So the salient point being not just, identifying when there are people, but it's identifying specific people. Like maybe what are the specific use cases or, that tie to specific kind of model classes, I guess?
So I think once the technology is in place, the possible use cases are endless. But right now we're focusing on 2 main ones. And again, I talked about both of these yesterday. So these are face recognition and scene description. So face recognition is basically finding out the name of a particular person based on the image of that particular person. And scene description is giving out a caption or a description for a scene which is within the image. Now, scene description has uses in home security systems because right now the home security systems are such that they alert you that there is motion detected outside your house or something is happening, but they don't tell you what is happening. And sometimes,
for example, the UPS is here with a package.
Yeah, so like our system can say, okay, the UPS guy is here with a package and it's dropped on your front door. Or like similar things like that. And again, face recognition can say if, like, say you saved your son or your daughter's face in your system, you know that they're coming home. And so the system just tells you, okay, this person has reached home.
Okay.
So that's another use case.
Okay.
Yeah.
Yeah, it's interesting. I think, at least for me, as you were describing, what you were trying to do, it's easy to get carried away and imagine like tons of use cases, but they're all, when you think through like the kinds of models that they would require, they're all really different. And so you have to really focus, at least now, on some very specific use cases.
Yes, that's true. But another thing is that in order to develop, say, even activity recognition, you need to have some basic recognition capabilities. For example, you need to define like what an arm is or any other body part. So that recognition capability comes from like what is possible again in face recognition.
Okay.
So what I'm saying
Elaborate on that.
Yeah, so that's basically like when you have one face recognition model in place, the only thing you have to do is tweak it a little bit to make it into activity recognition. Like in place of images in face recognition, you would need a time sequence or a frame sequence in activity recognition.
Are you talking here about transfer learning, meaning you've trained the model on faces and now you can use it to identify arms? Or are we talking more about sequence related things or something totally different?
I think it's something totally different.
Okay.
Yeah.
Great.
So what I mean is that once you have the basic capability in place, like being able to recognize faces,
right,
it is just parts of this algorithm or parts of this model that you would be reusing in other models like activity recognition. Now, you won't be using the exact same weights because that would be completely different. And you would have to retrain train from scratch the activity recognition model. But that said, the basic elements in both of these are the same, like the convolutions or the LSTMs.
Okay. Yeah. So you're saying you're building up the model architecture share a lot of common characteristics.
Yeah. Something like that, yeah.
Something like that, but not quite that?
I didn't actually understand what you said.
So the model architectures share a lot of common characteristics, meaning you're using the same general model architectures, the different types of layers, convolutional layers.
Yes. Yeah. That's a very easy way to explain it, yeah.
Okay.
I should have said that.
So, interesting. So, I guess what I'm curious about is you develop models. I'm assuming that the way that you would go about this is you want to develop facial recognition models. And you survey the literature, figure out what are the, best performing model architectures to do that, implement those, train those. And then you've got this model that probably doesn't fit on your embedded device.
Yeah.
And so there's a process that you go through to go from that model to one that fits. Like, walk us through, how much of that is art and how much of that is science, and walk us through like the thinking as you do that.
Yeah, sure. So this process is actually called pruning. Okay. So how you can go from like a big model to something that is just reduced to 11 times its original size. Okay. So the way to do this is, pruning basically has 3 different steps in it. Well, I think there are 3 different steps in it. Okay. So first is you need to statistically analyze your model to ensure that the weights follow a bell curve distribution, like a normal distribution.
No, I get that part. I think you're responding to me looking up like, okay, why is it important that your weights are distributed in that way?
Because when you're going to prune it, you're going to use some thresholds. Okay. Now, you calculate these thresholds using the standard deviation. Okay. And the assumptions of standard deviation are that it needs to be a bell curve.
Right.
So.
And is it typical or common that your weights do follow the bell curve?
Yeah, for all the models that I've tried it with, they almost always fall into a bell curve. Okay. Yeah. So once you know that it's a bell curve, you move on to the next step, which is the actual pruning stage. So you calculate the standard deviation of the weight matrices. Then you find the quartiles of each weight matrix. So that's basically standard deviation multiplied by 1, 2, 3, 4, and so on. Now, for each weight matrix, for example, if you're using a scene description model, that will have an image model and a language model. Okay. So for each of these, you will calculate their thresholds. Mm-hmm. Then you can remove all the weights which are less than that threshold. Okay. So like the first threshold you calculated, say it was 0. Mm-hmm. So any number less than 0, you can remove it.
Okay, so this is essentially a technique to identify and rank the contribution of individual weights in your model.
Yes, that's,
okay. Yeah. And so then you rank order these weights in terms of their contribution, and you have some cutoff, and you just remove the weights that fall beneath that cutoff. Now, I'm imagining when you do that, there are ripple effects in terms of your...
Yeah, that's why you need to load these weights back into the model.
Okay.
And then retrain it.
Okay.
Yeah.
All right. And then, so then was that your third step?
Yes. Okay. Retraining is the third step. Okay. Yeah.
Awesome.
And then you can basically repeat this entire process until you reach the most dense model.
Okay. And is there empirical work that shows that pruning leads to optimal compact solutions relative to, some other process that, maybe starts from a smaller, more compact model and trains those from scratch or something?
So there are actually different kinds of pruning strategies available. Okay. So I remember there are a couple of papers from Stanford that talk about this method. And there are a couple of papers from University of Washington and Allen Institute that talk about just removing one complete branch. Mm-hmm. So zeroing out everything in one convolution. Okay. And then retraining it. So it really depends on what kind of model you have and what results you want to attain. Okay. Yeah.
All right. Interesting. Can you give us a sense for the kinds of results? Well, you mentioned that your models after the pruning process can be like 10% of the size of the original models. What, in real numbers, like what does that tend to look like?
So if you talk about the scene description model that we worked on, its average inference time, it came down from 8 milliseconds to 2 milliseconds. Mm-hmm. And the accuracy also increased. So for scene description, there are different metrics like Meteor, Blue, Rouge, and Cider. So there was an increase of approximately 5 steps on these metrics.
Meteor, Blue, Rouge, and
Cider. Yeah.
Cider?
CIDER. Okay. Yeah. And BLEU. So these are some image captioning metrics. Okay. These are originally machine translation metrics, but they have been adapted to image captioning metrics. Okay. There's also a new metric called SPICE, which is used for image captioning.
Okay. And so you're saying that you can train a model, measure it against these metrics, prune the model, and then increase performance?
Yeah, because you will have a dense network. Like you can change some things in a network, like change the image model to something smaller and retrain it. And because you're starting from like trained weights, so you have a good initialization in your system when you retrain it. So that basically helps in going above the previously attained accuracy level.
And just to make sure I'm understanding, the previously attained accuracy level for an unconstrained by size model?
Yeah, that...
It's counterintuitive to me. The way I envisioned this is that, the best performance you're going to get is when you've got a model that's not constrained by, memory power, et cetera. And then you prune it and you make some compromises and you get adequate performance, but with a model with a footprint that can fit on your embedded device. And what I hear you saying is that you can actually increase your performance and shrink your model down at the same time?
Yeah.
Is that what you're saying?
Yes.
Okay.
Yeah.
Okay.
As an example of, again, the scene description model. So if you start from something like neural talk,
Okay.
that has a VGG network for its image model and a pre-trained LSTM for its language model.
Mm-hmm.
Now, if you remove this VGG network and replace it by something smaller like GoogleNet,
Mm-hmm.
and GoogleNet and VGGNet both lie within the same top 1% accuracy range.
Mm-hmm.
But if you use GoogleNet and the same pre-trained LSTM and retrain this entire system, you can actually get a higher accuracy.
And so for, folks that are doing research in this area and are, competing on accuracy, why don't they all just add another step in their process of pruning to come up with a better performing model, or at least try that?
Because I think that's not their main aim. Like, accuracy is their main aim, but pruning is not their main aim.
Right, but you're saying accuracy can improve because you prune.
Yes, that's true. But I know that because I tried that out as an experiment.
Okay.
So, I mean, if you're a PhD student, I doubt you will have time to experiment with pruning just for fun.
Okay.
Yeah.
And so so that I'm not making assumptions here, are you asserting that, maybe I am jumping to conclusions, and you're not asserting that increased performance or accuracy is a general result, as opposed to you just happen to see this.
It's not a general.
Time.
That's true. Yeah,
okay.
it's not a general result. It's not going to happen all the time. Yeah, it's not going to happen all the time. But there are some cases, like in this case, because the accuracy of both image models lies in the same top 1% range. Mm-hmm. That could be one possible reason why we're seeing the increase in accuracy.
Got it.
But if I were to use some other image model, the same results might not be repeated and the accuracy might actually decrease.
Okay.
Yeah.
That makes more sense.
Yeah.
Okay, so were there other things that you covered in your talk? So you went through your 3 steps.
Yeah, that's pruning. And I think that's about it. I mean, there were a lot of other things, but there's not much related to what we're talking about right now.
Okay.
Yeah.
What were the other things then?
So like for the face recognition pipeline, that is mostly 2 steps, like face detection and the actual recognition part.
Okay.
So can you improve on each one of these individually? Mm-hmm. So for face detection, if you use a standard library or a traditional computer vision system as opposed to something trained on neural networks, can you improve the accuracy, the inference time, and the model size? Mm-hmm. So for face detection, we saw improvement on all these 3 verticals.
Okay.
And on face recognition, we trained different models using somewhat similar architecture. Mm-hmm. So Google had released the FaceNet paper, which describes the NN2 architecture. So we built several models around the NN2 architecture and trained it with different input sizes, and saw that, there's different inference time, different accuracy that it attains, and different model size that all of these 2 parameters can change. So that's something that I also mentioned in the talk.
Okay, so the takeaway there is then that if you are developing a pipeline for something like facial recognition or some of these other, let's maybe generalize it to, if you're developing a pipeline generally and you want to get that pipeline to run well in an embedded environment.
Yeah, you want to be optimizing like each portion of the pipeline individually.
Right.
Yeah.
As opposed to just optimizing, being fixed on your end pipeline and optimizing that.
But that said, it's important to, like, after you're optimizing each little bit of it,
right,
you need to go over like a retraining step for the entire pipeline.
Okay.
That, like, this end step is, I think, the most important step.
Okay.
Yeah.
Okay. So you don't want to skip optimizing the individual pieces, but you want to, once you've done that, optimize the end piece. And is the idea that you start your optimization of the end-to-end system with better initial weights for the individual pieces?
Yeah, that's what I understand. Yeah.
Okay.
Based on like all the experiments that I've done.
Okay. Oh, interesting. Can you walk us through, we talked a little bit about VQA. Mm-hmm. Can you walk us through, is that something that you work on at Deep Vision as well, or is it?
So I think VQA will come in eventually because, like I said, scene description is something that we use right now, but eventually you would also want people to be asking questions to the system so that the system can give you an answer.
Okay.
Yeah.
And can you walk us through kind of what the current state of the art is with VQA? What are the approaches that folks are using and kind of generally how they take on that problem?
Sure. So I don't quite remember what is the state of the art now, but generally the approach is that you take an image model and you somehow interface or communicate it with a language model which takes the question as input. And when you're interfacing these two matrices together, the result will be a single vector, which will be the answer to the question that you have.
Okay.
So you can replace the image model with ResNet, Inception, GoogleNet, or basically anything, or like a combination of all of these. And the language model usually is an LSTM, or you can also have it as a bag of words vector, or any other representation of the text. Now, most of the work from VQA is coming from Devi Parikh and Dhruv Batra's lab. Now, they also started using reinforcement learning in this. So they're just trying to give adversarial answers and questions and having the other computer or the other agent within the same environment, trying to figure out which of these is incorrect and which of these is correct.
Okay.
So that's sort of like a brief overview of what's happening in VQA.
Okay.
Yeah.
Interesting. And there are some, I don't remember maybe you can remind us the name of them. There are some popular data sets that folks are using for VQA.
Yeah, it's called the MS COCO dataset.
MS COCO?
Yeah, it's released by Microsoft and it's the Common Objects in Context.
Okay.
Now, the images in MS COCO are actually really different from ImageNet because ImageNet focuses on one particular object in an image. And whatever the object is in focus, it usually occupies most of the area within the image. But in the COCO images, they're like normal scenes, like say this room, for example. It doesn't have a specific object or there's no specific person in focus. It's like random, not random, but scenes which have a lot of information in them. And in fact, there's also a release of the second version of the MS COCO dataset that happened this year.
Okay.
So that dataset actually fixes some of the errors not the errors, but actually the biases in the first dataset. For example, in the first dataset, if you had a number question like how many apples are on the table, most generally the answer would be 3. Or if the question is what color is anything, most generally the answer would be red.
And so if you train on this, you develop a model that overfits on 3s and...
So they actually trained like an image blind model, which never saw the images, only saw the questions and the answers. So this kind of model would just learn that if this is the question, this is the most probable answer.
Okay.
And even that performed considerably well. So that's
because
why...
of biases like
yes,
that.
Exactly, yeah. So that's why they developed the MS COCO version 2 dataset.
Okay.
Yeah.
Great. Awesome. Well, thank you so much for taking a few minutes to chat with me. I really appreciate it.
Thank you for having me.
And I didn't mention this at the intro, but we initially got connected because you listened to the podcast.
Yeah, I had actually listened to Chelsea's podcast, Chelsea Fens. Yeah, and that's how I really got interested. And I listened to, there was an NLP podcast from someone, I don't remember her name, but it was pretty recent around Chelsea's podcast. And I was like, wow, there's so many things that I don't know.
Okay, that was Ornitza.
Yeah, maybe. Yeah. It was a difficult name for me to remember. Yeah.
Awesome. Well, thanks so much for listening. And thanks very much for, spending some time.
Yeah. Well, thank you, first of all, for having this great idea. And thank you for having me today.
Awesome.
Thank you.
Thanks. All right, everyone, that's our show for today. Thanks so much for listening and for your continued feedback and support. Thanks to your support, This podcast finished the year as a top 40 technology podcast on Apple Podcasts. My producer says that one of his goals this year is to crack the top 10. And to do that, we need you to head over to your podcast app, rate the show. Hopefully we've earned your 5 stars, and leave us a glowing review. And more importantly, share the podcast with your friends, family, coworkers, the Starbucks barista, your Uber driver, everyone who might be interested. Every review, rating, and share goes a long way, so thanks in advance. For more information on Siddha or any of the topics covered in this episode, head on over to twimlai.com/talk/95. Of course, we would love to hear from you, either via a comment on the show notes page or via Twitter to @SamCharrington or @TwimlAI or @TwimlAI. Thanks once again for listening, and catch you next time.